Hello. What? Who just turned the camera on?
Good morning, all.
Morning.
Okay, so we got 16 of you here, so we'll just wait a few minutes longer until everybody gets here.
Nah.
Hey, so we're just missing 6 people. I'll just give them another 30 seconds. In the meantime, I've posted 2 PDFs to the Google Classroom. You'll be able to see them on my screen, but you might be able to see them better on your own screen. One of them is a booklet, which I've actually got printed up. I've got copies for all of you sitting on the shelf in front of me. So you can have that booklet when you come back into school. So we're going to be filling it in today. So maybe the best thing to do would be to just note the answers in the back of your exercise book today, and then you can fill it in when you get the copy when you're back in school. You're welcome to print it yourself at home, but it's about 8 pages, and I don't expect you to do that. It'll be waiting for you when you come back in. So you will just need the back of your exercise book to write some answers in today. If you haven't used Google Meet very much before, you might know that when I start presenting my screen, you'll be able to see the screen and a little thumbnail of this camera feed at the same time. And all you need to do to flick between the two is just click on the thumbnail. So if at any point you want to make the camera big, just click on the camera feed, and then the PowerPoint will go small. And then if you want to flick back to the PowerPoint, click on the PowerPoint and the camera will go small. At loads of points during the day, I will be asking you to unmute yourself and give me answers to questions. Please don't be shy, just do so. You can try and write your answers on the chat if you want, but my PC screen's about 2 meters that way, so I won't always be at it if I'm standing here looking at the camera. So I won't always see what you write on the chat at the moment that you write it. I have got the chat on the screen, so I can see what you write, but I might not be at the screen when you write it. Okay, let's make a start then. Oh, I've got 2 more customers. Who just turned up? Can you just, rather than me searching through the chat to find it, can you just tell me if you're here? Evie Allen? Jade Ashton? Kieran Riles? Will Simpson? Thank you, Will. And Jasmine Walker, are you here? Thanks. let's get going. It's going to be juggling between different screens, so give me a sec. Okay, so you should be able to see an atomic nucleus or a picture of one on the screen in front of you. Just unmute if you can't. Freddie, one of the PDFs is just answers to questions. That's the one that we're not going to need. Okay, so we've been spending a lot of time talking about the alpha, beta, and gamma radiation that comes out of the nucleus when it decays. And you now know lots and lots of properties about the alpha and the beta and the gamma and what they're useful for and what they're dangerous about and how we would recognize them. And we spent a lot of time talking about alpha, beta, and gamma. What we're going to turn our attention to today is what happens to the nucleus that emitted the alpha, beta, and gamma. We've been using this word decay rather than explode because it isn't truly an explosion. The nucleus isn't obliterated and ceases to exist. It's still there afterwards. It's just slightly different. So today's lesson and the next couple of lessons are about the nucleus that gets left behind. Okay, so here is the nucleus before it decays. And what happens is that in an alpha decay, you know that an alpha particle is a little bundle of 2 protons and 2 neutrons. And that little bundle of 4 particles leaves the nucleus. But all of the other protons and neutrons, they get left behind. And they're still a nucleus. They're not the same nucleus. It's smaller than it used to be. It's down a mass of 4, and it's down 2 protons amongst that. But it's still a nucleus. It's still got electrons around it, so it's still an atom. It's just a slightly smaller nucleus than it was before. So how would we capture that? So if I just flick to a different screen, hang on a sec. Okay, so the screen in front of you now, the first page of the one PDF, it talks about alpha and beta. We're just going to talk about alpha for a bit. We'll come back and do beta in a minute. So just ignore all the beta stuff. Right, so the first sentence says, an alpha particle removes how many protons from the nucleus? Shout it out or stick it on the chat. I can just about see it.
2.
2, very good. Okay, whoever just did that, you are going to bug me a lot. And when we get back into school, we'll be having a conversation. So let's be sensible, please, just like we would in class. Okay, the correct answer was alpha particle removes 2 protons from the nucleus. Thank you to the first person who spoke. Okay, the second sentence, it also removes something else, but that doesn't affect which element it is. So what also goes from the nucleus? 2 protons and also... Yeah, George, you're right. Neutrons, but how many neutrons? 2, perfect. Okay, so the alpha particle removes 2 protons from the nucleus, and it also removes 2 neutrons, but that doesn't affect which nucleus it is. So just make a little note of that in your book, so that you can copy it onto the printout when I give it to you. Okay, so scrolling down a little bit, we'll come back to the top bit in a second. There is an example on the screen for how we might summarize this. So it looks a lot like a chemistry equation, a chemical equation. And in a chemical equation, you've got the reactants on the left-hand side and the products on the right-hand side, and the arrow is pronounced turns into or makes or produces. So in this case, We haven't got a chemical equation because we're dealing with atomic nuclei, so we've got a nuclear equation. So we've got the nucleus of an element called radon, Rn, and radon is the proud owner of 219 protons and neutrons in its nucleus. And of those 219, 86 of them are protons. What's going to happen then is that the radon nucleus is going to decay. So the arrow in a nuclear equation is pronounced decays into rather than produces. So radon 219 decays into, and there's the alpha particle with its 4 protons and neutrons, and also of that, 2 of them are protons. And then what gets left behind are all of the other protons and neutrons. So there used to be 219, but 4 of them have left, meaning that there are only 215 remaining. There used to be 86 protons, but 2 of those have left as part of the alpha particle, and that leaves 84 behind. Now, in chemistry, you would have a periodic table and you would be able to look up element 84. But in physics, we're not going to give you a periodic table. You don't need one in the exam. You'll always be told what chemical it is. So PO is actually the chemical polonium, the element polonium. So you'll be given the PO bit. You'll just have to be able to work out the numbers. So if you just look at it as a maths problem, 86 is equal to 2 plus 84, and 219 is equal to 4 plus 215. You just need to be able to work out the missing numbers. So to practice that and see if you can do it, I have got for you 4 practice equations. Now, if you're looking at the PDF, your own copy of it, you'll notice that there are 4 more questions underneath this one. I don't want you to do questions 5 to 8 at the moment, just questions 1 to 4. So I'm going to give you 30 seconds, and then I'll do the first one with you. And then I'll give you another 90 seconds for the other 3. So race ahead if you want to, but I'm going to stop you in 30 seconds. Could you just have a go at the missing numbers, please? 30 seconds. Okay, so I'm not standing by the computer, so I can't see the chat. So if you could just unmute yourself and tell me what numbers should go here, please, for the element thorium.
Is it 234 and 90?
Perfect. Well done. Okay, so the uranium was the proud owner of 92 protons, but 2 of them left, leaving only 90 behind, and element 90 is thorium. The uranium also had a mass number of 238 because it owned 238 protons and neutrons. 4 of them left altogether, 2 protons, 2 neutrons, meaning that there are only 234 left behind. So the 90 tells you it's thorium, and this is the isotope of thorium-234. It's got 234 protons and neutrons all together. Okay, I'd like to do the other 3, and my 2 tips for you are to remember that alpha is always 4 protons and neutrons and 2 protons. So alpha is always 4 and 2. And remember, we only called it alpha when we didn't know what it was. And now we do know what it was. It's a helium nucleus. So you don't have to write helium if you don't want to. Sorry, you don't have to write alpha if you don't want to. You can write He for helium instead if you want. It means the same thing. So you can write alpha or you can write He. But either way, it's always 4 for the mass number, and 2 for the atomic number. Right, you got 90 seconds to try the other 3 questions. Okay, let's have a little look at the answers. So again, just unmute yourself and tell me what you think. So this is radium. This is Marie Curie's elements that she was using in her research. So radium has got 88 protons and 226 protons and neutrons altogether. 4 and 2 left, so what's that leave us behind? Shout it out.
Is it 222 and 86?
Yes, it is. Thank you very much. So element 86 is the element radon, not to be confused with radium. And radon has got 86 protons and 222 protons and neutrons altogether. 222 plus 4 is 226. 86 plus 2 is 88. Okay, next. Anyone know what element Pb is? The Romans used to call it plumium.
Lead.
It is lead. Okay, so lead is the proud owner of 82 protons and 210 protons and neutrons altogether. 4 and 2 left, leaving this element. Anyone know what element Hg is?
Mercury.
It is mercury. Very good. Okay, so numbers for mercury, please.
206 and 80.
Perfect. Again, 80 plus 2 is 82. 206 plus 4 is 210. Okay, this one's slightly trickier. You've been told what you made rather than what you started with, but I'm sure you can handle the maths. This is thorium. So tell me about the numbers for thorium.
Is it 330 and 90?
It is 90 and it is 30. Did you mean 330?
230.
230.
Very good. Okay, so 226 plus 4 is 230. 88 plus 2 is 90. Okay, there are a couple of little things that I want to point out on the board. So the first thing is there's some thorium up there, and there's some thorium there. That one's thorium-234. That one's thorium-230. Why is the mass number different? Have we made a
It's
mistake?
isotope.
Very good. So 2 different isotopes of thorium. So don't be worried if you ever do questions and find that the mass numbers are different. It's completely fine. Thorium comes in lots of different isotopes. Second thing that I want to point out on the board is that there's some radium and there's some radium. And this time, they're the same isotope of radium. So what I want you to appreciate here is that when the lead decays into mercury, this isotope of mercury is actually stable, and that's the end of the game then. So if I were to give you for Christmas a kilogram of lead, then over time, bit by bit by bit, the alpha particles come out, turn your lead into mercury, and bit by bit, your lump of lead will turn into a lump of mercury. And when it's all finished, that'll be the end of it. But if I were to give you for Christmas a kilogram of thorium instead, thorium-230, what'll happen is it'll turn itself into radium, but it won't stay as radium. While the rest of the thorium is still turning itself into radium, the radium is busy turning itself into radon. So some radioactive materials, when they decay, they turn into a nucleus that does have the perfect number of neutrons. And that's it. That's the end of the radioactivity. But quite a lot of radioactive nucleuses, when they decay, they still don't have the right number of neutrons, and they're still radioactive, and it carries on spitting out more and more particles until it gets to this perfect number of neutrons. So radioactivity sometimes stops and sometimes just carries on and goes again. And in fact, the radon is radioactive as well, and that'll decay into something else. Okay, third thing that I want to point out on the board. In a chemical reaction, we would call the left-hand side the reactants and the right-hand side the products. In physics, for nuclear equations, we don't really call them reactants because they're not reacting with anything. So instead, we've taken a kind of, I don't know, less rigorous kind of language, and the original nucleus is always referred to as the parent nucleus. And this is the radiation, that's already got a name, alpha, beta, gamma. But the nucleus that's left behind, you would think would probably be called the child, but in actual fact, for historical reasons, which are probably ever so slightly sexist, it's always referred to as the daughter. So I don't know where the language came from. I don't know why we use those words, but just like you know what a reactant and a product is in chemistry, I need you to know that a parent nucleus decays into a daughter nucleus, which is probably a bit messed up. Okay, so back up on the PDF, that's what goes in that little gap there. It says we call the original nucleus the parent and the new nucleus the daughter. So if you could just scribble that in the back of your book as well, so that we are ready to transfer it to your handout when you get it. Okay, we're about to move on to reactions for beta decay. And the nuclear reactions and the nuclear equations for beta decay are a little bit harder than the ones for alpha decay. So if there's anything on that board that you are a little bit hazy on or a little bit woolly on or want me to explain again, now's the time, because it's about to get slightly harder. I'm just going to give you 10 seconds to think about that. Unmute yourself if you want to ask me anything.
Sir, could you go over it again? I'm a little bit confused of what to do.
Yeah, so I don't know, let's pick this one. Radon is an element on the periodic table, and it has got 88 protons. And it's also got a load of neutrons, so that altogether it's got 226 protons and neutrons. we could work out the number of neutrons by subtracting the 88 from the 226. It's about to lose a piece of itself. It's about to lose an alpha particle because that's the bit that's going to come flying out of the nucleus as alpha radiation. So this nucleus is going to decay. A bit of it will come flying out, but the rest of it is going to get left behind. So when it does get left behind, it won't be 88 protons anymore because 2 of them left. So it'll be 86 protons instead. And it won't be 226 protons and neutrons altogether because 4 of them left. So there'll only be 222 left behind. So it turns out that element 86 is called radon, so we can write an Rn in there. And so what we've effectively done is we can see that the radium has decayed into radon, a new element, and it's done so by emitting some nuclear radiation, an alpha particle. So when you're doing the equations, you just need to make the numbers work. So you can see that 88 take away 2 is 86, and 226 take away 4 is 222. Or another way of looking at it, 222 plus 4 is 226, and 86 plus 2 is 88. So you haven't lost any particles, you've just split them into 2 different places. Some got carried away by the alpha particle, and some got left behind. And the key point here is that the alpha particle is always 2 protons and 2 neutrons. So 4 altogether, and 2 of them are protons. And you can call it alpha if you want to, or you can call it helium if you want to. We called it alpha when we didn't know what it was, and now we can call it helium when we do know what it is. It's up to you. Nobody cares whether you call it alpha or helium. Does that answer your question, or still confused?
Yeah, answered my question. Thank you.
Thank you. Tom, right, I can't see the board because you're sharing your screen. You should have a little thumbnail of the video that you can tap on the little thumbnail and it'll flick between the PowerPoint and the video. If you're on a phone with a small screen, I guess that might not be possible. Oh yeah, you can pin me as well. Freddie Young, this is your book and your notes. Make up your own title, but we're just making rough notes in the back of our books because all of this is on the PDF handout that I've printed for you, and you can just copy it into the printout when you get it. Grace Press, what are we writing down? You're writing down the answers that you will be adding to your booklet when you get it. Right, sorted. Okay, we're going to move on to beta now. So let me switch windows. Okay, that's the picture that we had for an alpha particle. We're on the screen now. Don't worry about the board. And you can see that there is a whole bundle of protons and neutrons, and then 2 of the protons and 2 of the neutrons left. And that's nice and straightforward for the alpha particle. But we know that a beta particle is an electron. Why is it going to make it difficult to draw a picture like this with an electron coming out of the nucleus? Don't be shy, just unmute yourself and throw it out there. So I've drawn 2
because they're so small, sir?
It is not because they're so small. I've drawn 2 protons and 2 neutrons coming out of a ball of protons and neutrons.
Is it because the electrons are in the nucleus?
Perfect. There are no electrons in the nucleus. So Welcome to the world of the very, very, very strange. About 100 years ago, we had to reinvent physics and create a whole new branch of physics, which is now called quantum mechanics, to deal with the weirdness of the atomic nucleus. So we need to kind of get something out there now. You need to understand that the nucleus isn't like everyday life. On the very, 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 very small scale of an atomic nucleus, the world is different. Things behave differently. So when was the last time you wandered down the street and walked past a parked car, and as you walked past it, the car pinged out of existence, and in its place was left a motorbike and a scooter? Or when was the last time you were wandering down the street and you saw some guy on the pavement walking towards you, and he just pinged out of existence, leaving behind him in his place two little kids running around? Or you get your lunch out to eat it, and you glance down at your sandwich, and it pings out of existence, and in its place is left an apple and a Mars bar. These things just don't happen, right? The world doesn't behave like that. But on a nuclear level, that's exactly how the world behaves. The nuclear world is fundamentally weird and very, very, very different to our meter-sized world. Remember, a nucleus is 10 to the minus 15 of a nucleus. And to get your head around that, a nucleus is as small compared to you as you are compared to the entire solar system. Imagine how much space there is in the solar system and how tiny you are compared to the whole of the solar system that's out there. If you wanted to go visit Pluto, it would take you 4 years in a spaceship to travel there. That's how far away Pluto is. And that's only a tenth of the solar system. The real solar system, with all the dust and gas, goes 10 times further than that. It would take you 40 years to travel from where we are now to the edge of the solar system. The solar system is really big and you are really small. And a nucleus is as small compared to you as you are compared to the solar system. And at that tiny, tiny, tiny little scale, stuff is weird. And what I'm showing you on the page, on the screen in front of you, is your first glimpse of this weirdness. I am not expecting you to look at that picture and go, oh yeah, of course, that happens all the time. Neutrons just randomly disappear from the universe, and in their place appears a proton and an electron. You are not supposed to look at that and go, oh yeah, that makes real sense to me, because it doesn't make sense. It's weird. But that's what can happen inside a nucleus. It is possible, although rare, it is possible for a neutron to just ping out of existence. And at exactly the same time, for a pair of a proton and an electron to ping into existence. It's weird. It doesn't happen in everyday life, but it does happen in nuclei. In particular, nuclei that have too many neutrons. We've spoken about this idea of having the perfect number of neutrons. And if you have too many or too few, you need to dump a few or gain a few. So the alpha particle is really good at dumping 2 neutrons, but it also dumps 2 protons at the same time, which sometimes isn't helpful. Beta decay is all about just losing a neutron. It just loses a neutron. Bye-bye, neutron. And in its place, it gains a proton. A byproduct is that it also gains an electron. The proton gets stuck in the nucleus. Remember, we have spoken about the nucleus being held together by neutron glue. And when one of the neutrons turns into a proton, all the other neutrons in the nucleus immediately glue themselves to it. So the proton that gets created, it can't go anywhere. It's stuck in the nucleus. So as far as the nucleus is concerned, all that happened was a neutron got swapped for a proton. And that's the key bit that you need to think about today. However, an electron did get created as well. Now, you might think to yourself, well, protons really like electrons and electrons really like protons. So maybe the electron stays inside the nucleus. But unfortunately, it's not that simple, because when the electron gets created, it gets created with a big bucket of kinetic energy. The electron gets created traveling practically at the speed of light, 95% the speed of light we spoke about. So although the protons in the nucleus really want the electron and are attracting it like crazy, and although the electron really wants the protons and is attracting them straight back, the electron's just traveling too fast to stay. It's a little bit like if you go outside and you throw a tennis ball in the air, the Earth attracts the tennis ball back again, and so the tennis ball goes up, but then it comes back. But did you know that if you could go outside and throw a tennis ball at 11 kilometers per second, now that's really fast to be able to travel 11 kilometers in a second. That's about 60 miles an hour. Oh, no, it's faster than that. Yeah, it's faster than that. It's about 60,000 miles an hour. So 11 kilometers per second is very, very fast. You can't throw a tennis ball that fast. But if you could, it would go up and up and up, and it would slow down, but it would never stop and it would never come back. It would be traveling so fast that it would escape the Earth. Well, same thing. That electron is traveling at 95% the speed of light, and it is traveling just too fast. And although the nucleus will try to pull it back, it won't be able to. That electron is gone. So the electron comes whizzing out of the nucleus, and we detect it as what we call the beta particle, but we can now call it an electron if we want. But we've dealt with beta, and we did that in a previous lesson. We're not going to be talking about the beta particle today. We want to be talking about the nucleus. So what happened to the nucleus? All you need to fix in your head is a neutron got turned into a proton. A neutron stopped existing and a proton started existing, so it's not quite the same thing, but it's okay to say in a test or in an exam, a neutron turned into a proton and an electron. Okay, so that's the picture I want you to keep in your head. Let's have a little look at what we should write on our PDF. Okay, so back to the top. A beta particle adds how many protons to the nucleus? Shout it out. Come on, you can do this.
Is it 1?
Very good, it is 1. A beta particle adds 1 proton to the nucleus. It also does something else involving the neutrons. What does it do to the neutrons?
Does it remove 1 neutron?
Brilliant. So a beta particle adds 1 proton to the nucleus. It also removes 1 neutron, but that doesn't affect which element it is. So in the back of your book, just add that the beta particle is 1 proton. It adds a proton, removes a neutron. Let's have a little look at an example of that. Okay, so I don't know if it's coming through properly on your screen. When I share my screen, the PDF goes a little bit weird. So when I'm not sharing my screen, there's an arrow next to the carbon, like there is for the alpha equation above. But when I share my screen with you guys, the arrow disappears for me. I don't know if you can see it on your screen or not. But there's supposed to be an arrow after the carbon. So there's the beta decay example. And what we've got there is that there is an element, carbon, which is the proud owner of 6 protons. And it also has 8 neutrons. 6 plus 8 is 14. And it's going to beta decay. And what that means is that when it beta decays, it's going to turn one of its neutrons into a proton. So you can see that the protons went up by 1. The 6 turns into a 7. However, the 14 doesn't change. because we lose a proton, but we lose a neutron, but we gain a proton. And the 14 is just the total number of neutrons and protons. So the neutrons went down one, the protons went up one. Overall, it cancelled out, and we've still got 14 protons and neutrons. Now slide your eyes across to the beta. When we wrote 4-2 for the alpha, like this, that really does genuinely mean that the alpha particle has got 2 protons, and it's also got 2 neutrons, so 4 things altogether. This genuinely is meaningful, and it's real, and it really is counting protons and neutrons. We write beta like this, and it's important that you understand that this is really just notation. It doesn't really mean anything. It's just written like that to make the numbers work. So if you look at the example, 14 plus 0 is 14, and 7 minus 1 is 6. So these numbers really do mean something for the alpha particle, but for the beta, it's just a little mathematical reminder so that we get the sums right. So some of you will remember a neutron turns into a proton, and that's the way that you will do beta equations. That's the fact that you will remember in your head. Others of you won't remember that. You'll get muddled up. Is it neutron to proton or proton to neutron? And you'll find that difficult to remember. So for those of you that can't remember neutron to proton, maybe you'll do better remembering this, 0 minus 1. And if you can remember the 0 minus 1, you can just do it as a sum. 14 plus 0 is 0. 7 minus 1 is 6. You can kind of see that it kind of means something if you stretch it a bit. So this is the mass number. And we've already said that beta doesn't really have any mass. Electrons don't really have any mass. So writing the mass number as 0, it's not really a lie. An alpha particle doesn't really have any mass. Oh, sorry, a beta particle doesn't really have any mass. The minus 1, how would you interpret that? Well, it's basically saying that the electron, the beta particle, used to have a proton, but it's kind of put it down somewhere and lost it. So it's lost a proton, which kind of is what happened. The electron did have a proton when it was inside the nucleus, when it got created, but then the proton got locked inside the nucleus and the electron left. So I guess kind of the electron did kind of lose a proton. It did leave it behind in the nucleus. So you could kind of say lost 1 proton. Bit of a stretch. Okay, we're going to try some equations to see if you can do this. So if you scroll down the page a little bit, if you've got the PDF open yourself. So there's 4 more questions, questions 5 through to 8. And like last time, I'll stop you after 30 seconds just to check that question 5 is okay. And then I'll give you another 90 seconds for the rest. But if you're feeling confident, feel free to race off and do all 4 of them. So 30 seconds to get number 5 done, please.
Sir,
Yeah.
Tom wrote in the chat.
Okay, give me another 15 seconds, Tom, and then we'll go through the first one on the board. Sorry, I was muted. Okay, let's go through this one to check that we're all okay with the first one. So thorium is the proud owner of 90 protons. And it's also got some neutrons as well, 144 of those. So altogether, 234 protons and neutrons altogether. What's going to happen in the beta decay is that one of the neutrons is going to turn into a proton. So there used to be 90 protons, and we're about to get one more because a neutron is going to turn into a proton. So that's going to go up to 91. But the total number of protons and neutrons is going to stay the same because we lost a neutron, but we gained a proton. So it cancels out. So we used to have 234 protons and neutrons. We've still got 234 protons and neutrons. Admittedly, one fewer neutron, one more proton. Right, Tom, does that help at all? You can write in the chat if you've not got a microphone. Okay. My top tip for the others, like the alpha particle, remember beta is always 0 minus 1. So you can just go right down the page, writing 0 minus 1s in. And again, you can call it a beta particle if you want, or you can call it an electron if you want. We called it beta when we didn't know what it was, and we call it electron now that we do know what it is. So you can use beta or E. It's completely up to you. Okay, 90 seconds to finish off. Another 30 seconds. Okay, who wants to unmute and tell us about bismuth decaying into polonium via a beta particle? What are the numbers for the polonium?
Is it 234 and 91?
I think you've just done the first question again, the protactinium.
Sorry. Is it a 214 and 84?
Correct, thank you very much. So the total number of protons and neutrons hasn't changed. It was 214, it's still 214, but the number of protons has gone up one because a neutron has turned into a proton. Or, if you want to go at it mathematically, 214 plus 0 is 214, and 84, take away 1, is 83. Okay, the protactinium from question 1 is still radioactive, and it is going to decay again, this time into uranium. Somebody tell me about uranium. How many protons and
2, 3, 4, and 92.
Perfection, well done. Okay, so again, total number hasn't changed, but a neutron's turned into a proton, so the protons have gone up 1. Or 234 plus 0 is 234, 92 minus 1 is 91. Okay, what about this one? So cobalt has decayed into nickel. What must the cobalt have looked like at the beginning?
Is it 60 and 27?
Perfect. So we've gained a proton because a neutron has turned into a proton, but the total number has stayed the same. Or mathematically, 60 plus 0 is 60, and 28 minus 1 is 27. Most people find the beta equations trickier than the alpha equations. So what I would suggest you do is, you've probably noted these answers down in the back of your exercise book. When you get the handout, when you're back in school, rather than just copy the answers into the handout, it might be worth doing these questions again in a week's time when you're in, just to check that you still know how to do it. Okay, those are the nuclear equations for alpha decay and for beta decay. And so you might have noticed, if you've been looking in the book yourself, that there is no equation for gamma decay. So this is what gamma looks like. Why do I not need an equation for gamma decay?
Is it because it doesn't come out of like a nucleus?
Well, it does come out the nucleus, but what doesn't come out of the nucleus?
Does it not take anything away from the nucleus?
Correct. It's emitted some energy, but it hasn't taken away any particles. So the nucleus is still exactly the same as it was before. It's got a little bit less energy than it had before, but it's still the same nucleus. So we don't actually need to do any equations for gamma because nothing happens. Okay, let me show you one more. Okay, we have got about 7 minutes left, something like that. This is the double-page spread from the Caboodle textbook, which covers what I have said today. So what I would like you to do for the time that remains is to skim read over that to make sure it makes sense to you. In particular, there's a tiny little bit on the second page in the middle that under the heading neutron emission that I haven't spoken about, but it's just a couple of sentences and you can read that for yourself. And then there are 4 questions. Now, if you were here in school, I'd set those for you to do as homework. I'm not going to set you homework to do while you're at home isolating, because I think it's pretty tough for you to make yourself sit at your desk for 5 hours every day and do this work on your own. I think that's hard. I'm not going to add homework to that on top. But what I would say is that if you find yourself on a day of isolation where maybe you don't get set 5 lessons work, because it'll happen, if you find yourself with a hole in your schedule and you don't have anything to do, rather than waste that time, come back to this PDF, please. Make sure that you have finished reading through it and make sure you get those 4 questions done. I imagine you will have a 15-minute window at some point through a lost lesson over the week that remains. So just come back to it when you get a chance. You've got 5 minutes now. We're going to end the meet in a second. And you've got 5 minutes now. That might be long enough to read it and maybe do one of the questions. But try and get all 4 done if you can. But it's not homework. You won't get a caution if you haven't done it. However, on that note, let me share another screen with you. Stop sharing. Wrong one. This is the homework that I set you to be done by Sunday, 2 days ago. And you'll note that there are 9 of you that have not done it. So I'm not going to be mean enough to set you a homework caution while you're at home isolating, but I want that done, please. So if you are one of the 9 people on that list, get it done today.
No, that ain't our class.
That's not your class. Okay.
No.
There are 9 of you in your class as well, I think. Oh, no, it wasn't. Oh, I've just moaned at the wrong class. You guys have done it, haven't you? There's... Oh, where's it gone? Homework. How many of you? Oh, no, there's still people not done it. Oh, no,
Still not our class.
That's not our class.
You need to get yourself a better teacher. I'm just incompetent. Homework. Oh, Freddie, it's just you. What's going on, Freddie? Get it done, please. Okay, I will see you later in the week for another lesson. Like I said, if you've got spare time, have a look through the PDF, do those 4 questions, but it's not compulsory. It'll just be good for your soul. That's it. See you later in the week. Kieran, you're still here. Are you still here? Or have you in fact logged in and wandered off?